Hi, I'm April Snyder. I am a concrete petrographer for 20-something years, and I'm currently working with ECS. I've had a lot of experience with the pyrrhotite issue, going back to when it was first identified in Quebec. And I wanted to talk about some petrographic techniques that we use to identify and determine the relative abundance of the mineral in concrete. So just an outline of the presentation. I'll go through a background of why we're looking at this, why we care about this. Identify the sample preparation techniques we're using, and then the two different primary methods for detection, which is reflected light microscopy and scanning electron microscopy with X-ray mapping. So just to talk about why this is an issue for those of you who may not be familiar, there are thousands of concrete foundation structures in Connecticut, Massachusetts, and the Trois-Rivières portion of Quebec that have been affected by pyrrhotite-induced distress. So pyrrhotite and other iron sulfides, they can oxidize in concrete. They release sulfuric acid, create secondary expansive products, and result in what we call internal sulfide attack. And in the most severe cases, I've had samples where I can literally crush the concrete with my hands, which was so fun to to do whenever I realized that. Although it's not funny, but it was it was fun. The issue is that the sulfur content in some of these homes that exhibited damage was less than 1%, and reported and visual damage was identified in concentrations of like 0.2%. So you see that it can cause damage at very low concentrations. In Connecticut, most recently, they've identified at least 35,000 homes now, built between 1983 and 2015. And Massachusetts has confirmed sources with three different quarries and that have damage confirmed currently. So what has happened in the last few years is that Connecticut has initiated legislation for regulation of iron sulfides in aggregates. So if you're a concrete producer, you have to test your aggregates for total sulfur, identify how much is there. If you have sulfur above 1%, then your aggregate's rejected outright. If it is less than 0.1%, it's accepted. But if you're in that range of 0.1 to 1%, you need to take a look at the iron sulfide content in your aggregates to see where that sulfur is coming from. There's a couple methods that are developed or used for that, and in the legislation particularly, they have identified acceptable techniques using magnetic susceptibility, and there is, I think it's Trinity College, has developed a technique for that. It's kind of specialized, not a lot of people have experience with that, but it is available. The other technique they identified is X-ray diffraction. So X-ray diffraction is a great tool. It's a wonderful tool to identify the crystalline components in anything, and in this case in concrete or aggregates. The issue with that is that the detection limit is generally identified as 1 to 5%. And again, we're looking at concentrations down to 0.1%. I don't want to say that it can't be done by XRD, but you really need some optimal conditions, specialized equipment, in order to get that identification that low. So when you're talking about, you know, the general industry, you want to send it to a lab, do XRD, for the most part, they're not going to be able, you know, to do. You're going to be very limited on what labs you can send it to that only want to test their, use their XRD for detection of pyrrhotite, and that's going to be hard to come by. The next method is a petrographic analysis. And generally speaking, for petrographic analysis of concrete aggregate, we use a test method, C295. And in that test method, it starts with looking at aggregate particles. Well, first you separate by the sieve sizes, and then you're looking at aggregate in a microscope, a stereo optical microscope, and separating based on really hand sample petrography, you know, what's it look like, what are the grains, what's the color, what's the hardness, texture, different things like that. And that can become difficult as well when we're investigating the amounts in you know, less than 1%. Oops. So to give you an idea on you know, what are iron sulfides for those of you who may not be familiar with it. So these are common accessory minerals that come in a variety of forms. We have pyrite, which is the most common. Marcasite is a different form of pyrite that's actually more reactive. We have pyrrhotite, and I do have pyrrhotite is the most problematic in concrete. And that is the mineral that is causing the structural damage in these concrete foundations. So when we talk about, you know, C295, and I wanted to just talk a little bit about why that may not pick up the present in aggregates in such small amounts. You know, what I found is that if you have pyrrhotite in about 0.5% or more, you will find indication of potential iron sulfide for the fact that you'll probably end up with some rust staining. And if you see rust staining, you're like, oh, we better check for iron sulfides in that. So you may look a little closer. Depending on how big the mineral is, it may be easy to distinguish if it's pyrite or pyrrhotite, if they're big enough. Pyrite is hexa. I'm sorry, I can't even see my own writing. Pyrite is cubic, right? And it is hard. It has a hardness of about 6, where pyrrhotite is a lot softer. It has a hardness of around 4. And it can come in a variety of different forms. It can be a prismatic barrel-shaped, tabular, platy, bladed, can have hexagonal rosettes. And so that can give you some indication, but the grains have to be pretty big for you to see that with your standard C295. And this just gives you an indication of what I'm talking about. So the image here, this is a core that was taken out of a concrete foundation, and we slice that core in 1-inch slices, so you have a cross section horizontally. And you can see the coarse aggregate. And these little particles here are where we have some iron sulfide inclusions, okay? And in this case, it's pretty visible, right? This is a photograph. we can see that with a naked eye. If you go to this grain in particular, you're looking at this little guy here, and you bring it over, and this is less than 1/2 millimeter in size. Now, if you notice, this is inside of the outside of the particle. So if we're doing our standard C295 and we're just looking at the grains, if it's not rust colored, rust stained, if you don't have that mineral on the outside, it's going to be really hard to know if there's actually an iron sulfide in there. So that's the first complication. But then you look at, here's the grain. Ooh, sorry. Here's the grain that we're looking at. And we have 3 different, and this is in backscatter electron imaging. And we have 3 different iron sulfide minerals that are present here. There is a chalcopyrite, there's pyrite, and then this is all pyrrhotite, and it actually has already been weathered, so it is showing oxidation corrosion, which also alters what it looks like here. So it can be very complicated. So when we started investigating the aggregates out of Connecticut to do the total sulfur, to see if they contain pyrrhotite, China used the standard C295. We got our total sulfur measurements. Some of them 0.12, right? 0.13. We didn't see anything. There's no rust staining. Once you get about, like I said, about 0.5 or more, we might have rust staining, so we have some indication. But we need to define if it's there or not. So in this case, this technique for looking at the concrete, when the issue was being investigated in Quebec, there was a whole consortium of experts who developed a technique to try to identify, document how much of the minerals present in that aggregate source, and how can we quantify it. So they used the total sulfur aggregate, the total sulfur amount, and then what we did was, what we did was, for all of the coarse aggregate, because that was the aggregate in question in this case, we scanned the sample and numbered every aggregate. So then for each of those aggregates, we looked at the number, we did like a visual assessment to see, okay, it's taking up about 3% of that aggregate, that one aggregate grain, or maybe 0.5% of that aggregate grain. And then we go look at it in detail. At that time, we were primarily using reflective light microscopy, which I'll show you in the next slides. And doing a relative visual relative estimate of how much of each of the different iron sulfide components are present. And then that would be tabulated. You got a total at the end, and then they were able to calculate how much of that sulfur that they found can be attributed to each of the different mineral types. So when we came to the Connecticut stuff, and now we're just looking at aggregate and not concrete, I thought, why don't we apply that same kind of technique to look at the aggregate? So that's what I'm going to talk to you about. So what we did was come up with a sample preparation technique to prepare the aggregate samples for this kind of evaluation. Accurate characterization of iron sulfide minerals really start with the sample preparation. It's very important. Each stage, whether you're starting with the mounting, the grinding, the polishing, it's all very important. So I am going to spend some time showing you about that. So what we did was we used PVC pipe that you get at the Home Depot or Lowe's or wherever. For the coarse aggregate, we're using 4-inch diameter pipe, and for the sand, we would typically use a 2-inch diameter pipe, and you're going to get a lot of grains in that cross section. So we're going to put our aggregate in there, try to do like a real nice flat. We want to get as flat as we can in that pipe, and then we are going to use a low viscosity epoxy to fill the spaces between the aggregates. Sometimes we vacuum impregnate if we're looking at a porous aggregate, like the schist that we saw in Connecticut, to really get a nice suitable sample for polishing. So one side of the mounting board, we do use like a sticky mounting board to prevent the epoxy from seeping underneath of those PVC pipes. So we're first going to grind the material, starting with something really coarse. An 80 grit silica carbide typically is used on the wheel to do quick and controlled grinding. So what we're trying to do is grind through all those grains. So if we have, for the sand, we can have, hundreds of grains that we're going to cross section. Obviously, for the coarse aggregate, depending on the size, we can have 50, or we can have 5, if it's really big. But anyway, we want to cross section everything that we have mounted in there so that we can see inside of the aggregate grains. So finally, we want to polish this to a real fine surface. So we'll start with a diamond suspension spray on the steel and copper polishing discs, and move to really fine fabric pads for the final steps. So it's really important to get reproducible, repetitive, and consistent motions when you're doing the polishing, so that we get a good surface for evaluation. So, that high quality preparation is really critical for the detection and interpretation of these minerals. It's also important to note that they do oxidize pretty quickly. So you either have to analyze it pretty fast, or we put it in a vacuum oven to keep air from getting on it if we can't analyze it quickly, because it will tarnish, especially the pyrrhotite. It'll tarnish pretty quickly, within a day. Yeah. 2 minutes? Uh-oh. I talked too long. So for the reflected light microscopy, we used a Zeiss Axioscope 5 polarized light microscope. It was equipped with the reflected light bright field, and a nice camera with some imaging software. And what you see is that this is the most common tool for looking at iron sulfides and recognizing them as a reflected light microscopy. So the pyrite is a yellowish white color. It has a weak anisotropy. Pyrrhotite is really strongly anisotropic. It has more of that creamy brown. The pyrrhotite is more the creamy color with a little bit of pinkish to it, and we commonly see this pitting that you see with the pyrrhotite, because it is softer. The pyrrhotite's really going to have a higher relief. So, but anyway, this is the standard, the gold standard for looking at iron sulfides and identifying them. So we're going to put that into scanning electron microscope. We are using a Thermo Fisher Chemisem microscope in backscatter electron mode. And what you can see is if you play around with the brightness and contrast, you're going to be able to see, these are all made of, the same elements, iron and sulfur, but if you change, they have different amounts of each. So if you mess with the brightness and contrast, you will be able to see a difference between the different ones. So the instrument we've been using actually has a phase mapping capabilities, and so it worked really great. I was super excited because sometimes those automatic phase mapping programs in the SEMs don't work really well. This was wonderful for iron sulfides, and we were very excited for the results. It shows you the different phases, and then even gives you an area percent. So now instead of our, with petrographic exam, everything's qualitative, right? We're guessing, we're having an educated guess on how much area space something is making up. But this is great because it gives us some numbers that we can feel, really confident, and we can see things that may be a lot smaller than you can with your naked eye. So this is just showing you the different elemental spectrums that correlate with the minerals, and you'll see the pyrrhotite, the iron is a lot higher than the pyrite, almost twice as high typically. We found some chalcopyrite and also some pentlandite. So the chalcopyrite has the copper, pentlandite has nickel. So this is the second area that we looked at, and just showing you again, did the same kind of thing. We were able to identify all the different components, and you compile the data. You can take as many points as you want, depending on how much you're seeing there, how robust you want your data set to be, and then you can come up with an average, a relative abundance of each of the different mineral types. So then that can be used for calculating your weight percent of each mineral from your total sulfur. You can also use this in your C295. So we've done that before too, where we did a C295 and just mounted each size fraction and counted how many aggregates have iron sulfides in it. And we've done it both ways, where you just did our standard 295 versus this one, where we're actually cross-sectioning each mineral, and there's a big difference on the results that you're going to get on how much is present. And that's it.